Okay.
Okay, it's a real privilege to introduce Yoshua Bengio from University of Montreal. Something that you may not know is that he did his PhD on deep networks for speech recognition in 1991, and says that they still work pretty well. But he and his students have learned lots of new ways to train things that make them work even better. It doesn't hurt that the computers are a lot faster as well. When he was doing his PhD, I was an undergraduate, and that was the second time that neural networks were hot. And so I was very interested in them and taking neural network courses and so forth. This is a time when Paul Smolensky was doing neural networks, when Michael Jordan was doing neural networks. In fact, Yoshua did his postdoc with Michael Jordan at MIT after that. And then was at AT&T before ending up at Montreal. So he has Canada Research Chair and lots of awards, and is on the editorial boards of lots of journals, and has been program chair and general chair of NIPS. And I would say that together with Jeff Hinton and Jan LeCun, he's one of the people who have really brought neural networks back in this third resurgence of excitement when they're actually being picked up by all kinds of areas of engineering, and Google is buying neural network companies for hundreds of millions of dollars. So we're looking forward to what he has to say, which combines two of his abiding interests over the years, namely how to use the tension between generative and discriminative modeling and networks. Thanks.
Thank you, Jason. And thank you for having me here today. So I have only less than an hour, so I'll skim through a few things. And please don't hesitate to interrupt me in the middle and ask questions. I much prefer that. So let me start with some general notions. Tell you a little bit about some of the motivations for what we're doing. Jan LeCun and I created this conference called International Conference on Learning Representations. And we think that learning representation is one of the really important aspects of machine learning that has been overlooked until recently, and that there are lots of advantages for doing that. And this slide illustrates one of the early ideas that as we know, when we're using machine learning in applications, the results we're going to get are very strongly dependent on the kind of feature you use as input. And so it would be great if we have machine learning methods that find the features for us. And that's one way to think about what representation learning is, but it's actually much more than that. As the second part of the slide shows, it's also about making sense of the data and trying to figure out how the data came about and what are the underlying generative factors and causes that could have produced the data. So good representations have to do with good guesses at what are the underlying causes and factors. And these two things are related. This is traditionally sort of the discriminant supervised learning kind of framework. And when we think about learning representations, we can also think of learning them in an unsupervised way using, for example, generative models. And the second half of my talk will be about that. Having good representations makes a lot of sense in many cases, and there's an example that you probably use without knowing, and that is Google image search, where you combine representations for queries, which are short sequences of words, with representations for images. The two representations live in the same space, like a 100-dimensional vector, and you simultaneously learn representations for the words and representations for images, such that representation for an image comes close to representation of a keyword that is associated to the image in the logs of people clicking on images after typing a query. And by the way, this is mostly the work of my brother Sami, who's at Google Research. Since there are a lot of people interested in natural language processing. Here I thought I would say a few words about some of the things I've contributed to that's connected to deep learning, but that came before. And that is the idea of learning representations for individual words as part of a language model. So I actually came here at Johns Hopkins about 10 years ago to talk exactly about this. And so in those days, what it was about was learning to predict the next word in the sequence of words given the previous words, using a very straightforward neural net, with the only kink being that the first layer of the neural net is just mapping the word symbols into these vectors, one vector per word. So it's just looking up in a table and using the same table for all the words at different positions. And otherwise, it's just trained as a regular neural net. And why we were interested in this, because I thought that there was something wrong with n-grams and other non-parametric methods for both language modeling and in general for machine learning, in that these kinds of non-parametric methods wouldn't generalize to new configurations naturally. Whereas what happens here is that once you map the words to this distributed representation, what happens is it will automatically generalize what it has learned for configurations of words to other configurations of words that have similar representations. And in this way, there's a kind of chicken and egg thing happening where the representations of words that come up in the similar context will end up being similar, so long as they help you predict the next word properly. And you get potentially exponentially more powerful generalization, and I don't have time to talk about it here, but I've written a few papers about how distributed representations in general can, in theory, bring you an exponential advantage in terms of the number of parameters you need to represent a complicated function. So I guess many of you have seen these. You can take these high-dimensional vectors, well, like a few hundred-dimensional vectors, and reduce their dimension to 2, so you can visualize them. And then you zoom in, and you see that the words aggregate each other in a semantically meaningful way. So here, there's a cluster of words about countries, and you can spend hours looking at these things, and they're fun. Here you see verbs and conjugations of to be and things like that. But something really cool came up recently that some of you know about that I want to mention that has to do with learning of these embeddings. And that's essentially coming from the work of Thomas Mikolov, first when he was at Microsoft and then at Google, where he's noted as a kind of unexpected side effect that these word embedding, these word vectors, had some kind of analogical properties. So if you take the representation for Paris and Rome and France and Italy, and you look at them, you see that the vector going from Paris to Rome is aligned with the vector going from Rome to Italy. And so now you can do things like Paris minus France plus Italy, and it gives you something pretty close to the vector for Rome. Similarly, if you do king minus queen, it's about the same as man minus woman. So why is this interesting? It's because you are, when you take difference of vectors, you're getting something more abstract, which allows you to reason by analogy. Now, you can train machine learning systems to do these kinds of things, but the really amazing things here is that this was not achieved through supervised learning of analogies. This was achieved by just doing language modeling in a completely unsupervised way. And that's really surprising. And that's something we need to understand better, why it's happening and how to generalize this. One of the issues we faced initially with the kind of neural net language model learns embeddings is that the output of the neural net is huge. It has as many output units as the number of words in the vocabulary. So in the experiments I run, I was limiting myself to something like 10,000. But of course, for real language models, you wanted at least 100,000, and Google wants millions. So there are a bunch of techniques over the years that people have looked at to try to reduce that computational bottleneck. When I actually came here at Johns Hopkins, I presented this idea And then we implemented it in the paper that came out in AI Stats a couple of years later, where you organize the word into some kind of hierarchy, a tree structure, and then instead of predicting the words directly, you predict the parent structure. So you predict which word class the word belongs, and within the class which word it is. And each of these predictions is small. So if you have two levels and you organize it well, then the number of children you have to look at is only an order of the square root of the number and size of the vocabulary. And if you do it on a binary tree, you can go down to log n. So it's pretty drastic reduction in computation. And this is actually how current state-of-the-art models using neural natural language models are doing it. And there are other methods that we played around over the years and other people looked at where you use sampling methods in order to reduce the computational burden. So instead of trying to, when you train these nets, what are you trying to do? You're trying to make the output of the correct word larger and make the output of the other word smaller. So you always want to, clearly you want to maximize the output of the correct one, but maybe you don't need to visit all the other ones for every example. You can sample negative examples. And that's essentially what all of these methods do. You can use important sampling tricks. You can also use some uniform sampling in a family of criteria called stochastic contrastive criteria. Basically trying to push up the correct answer and push down a randomly chosen incorrect answer. And even though
give you the correct expected gradient.
So this doesn't allow you to get an estimator of the probabilities, but it still works. So it gives you very good embeddings. And it still gives you, if you wanted to do something like classification or whatever, this still works. So it doesn't learn a probabilistic model of the sequence of words in a way that we can interpret it easily, but it does work in the sense of learning good representations. And in some cases, that's all you need.
And the importance of the method.
Yeah, these give you proper estimators of probabilities. Yeah. But this is so much simpler. All right, so let's get back to depth. So this is one of the things that I would say makes a difference between what we did in the when I did my PhD in the late 80s and early 90s and what we have been doing in the last 10 years now is trying to find better ways of training deeper neural nets, both supervised and unsupervised, both discriminant and generative. And there's a lot that's being written already, and there's probably a lot more to be done on the theory side to understand why having these multiple levels of representation could be useful. And the basic idea is that you can think of it like factoring a polynomial. So you can represent a polynomial as a sum of products, and it could be a very, very long polynomial with many, many terms. But maybe you can factor this polynomial into something that's much simpler to write down. And if you can do that, then you need much fewer parameters in order to train it. That's what deep learning is about. It's trying to find a kind of factorization of the function you want to learn into this composition of simpler functions. So if you can learn a composition, and it turns out that your composition of simpler function fits well your data, then it's more likely to generalize better. Simply because with a kind of simpler structure, you're able to explain more, even though the final function could be very complicated. I mean, it may look complicated, just like you take a product of polynomials and you multiply them, it ends up being a huge polynomial. It can have a huge number of ups and downs as a function. So the number of variations that it can capture can be exponentially large with the depth, yet the number of parameters can remain small. Whereas if you have a shallow architecture, you basically need as many hidden units or as many RBF units if you're doing an SVM as you have variations or ups and downs in your function. Okay. Then there's, of course, the biological motivation, especially when we know about the visual cortex, clearly suggests that the brain is using this kind of composition of nonlinear transformations and nonlinear relationships. There's also similar kind of arguments that can be made by looking at how we think from a cognitive point of view. More recently, and I'll say a few more words about that later, there's a motivation from the point of view of sampling methods for generative models. So it turns out that sampling in general probabilistic models is difficult, and the most general methods based on MCMC can in principle do everything, but they can be arbitrarily bad, arbitrarily high variance. And as I mentioned later, if you sample at the higher levels of representation, you can actually get these methods to work a lot better in the sense of better mixing. And of course, the real reason why people got so excited is because they found that it worked so well. And it's been applied to a bunch of things, most notably object recognition and speech recognition, but also language and music modeling. And the press has been picking up on that, and I guess this slide is already getting old. It's more, I'm not going to bore you with that. And the MIT Technology Review last year decided to put deep learning as one of the 10 breakthrough technologies of 2013. I mean, they were late by 6 years, but that's okay. So some of you, I'm sure a lot of you know about how speech recognition has been influenced, changed by the advent of deep learning, but I find this graph really amazing. So these are years, and the y-axis is word error rate on switchboard. And what happened in the 90s is that we made a lot of progress, both due to better algorithms. I mean, it was always GMM, HMMs, but essentially being able to train bigger models faster and so on. And then in the next decade, even though computational power continued to increase, models continued to be bigger, there wasn't so much progress. And then deep learning came. So that makes people pay attention.
Yoshua, why do you think there wasn't progress during these times?
Well, I was busy doing something else. I think so. When I finished my PhD and I considered what I would do next, I thought speech recognition, the speech recognition area was going into kind of a local minimum where people were just doing very small tweaks, and I wanted to do something a bit more risky and ambitious. And I think that's a general problem in many areas of science, especially engineering-like sciences, where we can get stuck in an area of the space of algorithms. And so we have to take risks at some point and try things which don't work initially. So that's.
I'm not sure that slide is entirely accurate.
It sounds like a Microsoft view.
Yeah, those numbers come from Microsoft.
Oh,
Blame them.
You know what the big trick they did is? They started testing on a different subset from what people have been testing before.
Oh.
So really there's not more than like 10 or 20% relative improvement. So I wouldn't show that slide again.
Yeah.
Okay.
Especially not.
I mean, there has been improvement, but it's nothing like that.
Okay. Well, it depends on which data set you test, of course, right?
No, but look, I don't know where these numbers come from, but the reality is there's like maybe 25% of it.
Okay.
It's real, but it's not like
Well, thanks for the information. So I'm more certain about these numbers, and that's in computer vision, object recognition. So there was another breakthrough happened a couple of years later than the speech recognition breakthrough, and there's an interesting story here with people in the computer vision community telling Jeff Hinton and Yann LeCun that they would believe deep learning if they could make a breakthrough in a large object recognition task like the ImageNet competition. And so they did. And brought the error rate down by almost half. The current numbers are, I think, around 12%. So it's now down by more than half. Using a convolutional deep net with all kinds of variations that are now become standard, and that many of them are actually used also in speech. This has been picked up by, of course, companies like Google and Baidu in their products. Just want to mention a much smaller feat that my students achieved just recently, a few weeks ago. We won a competition, computer vision competition, where you had to go from videos of clips from movies where you see the face of an actor into classifying the emotion, the expression on the face of the person, and we were able to win by a reasonable margin over the other techniques. Actually, one of them was also using deep nets. There's a more interesting question that's actually now starting to move towards the theme of unsupervised learning, which is, how do humans generalize from very few examples? How do they manage to do that? It's amazing. I show you just one or two examples of a new category, and you can generalize quite well. And of course, all of the machine learning we know, including deep nets, they're pretty bad at that. And so the only reasonable answer is because they're exploiting all of the other learning that's been done before to build some kind of representation of how the world works, so that it's almost like if this new example, you're not doing any learning, you're just doing inference, right? Based on that new piece of evidence, you can guess all kinds of properties that were missing for that example. And that's just almost as there's no learning. So it relies completely on all the past learning, and I think it relies on learning abstract representations. And to obtain abstract representations, I think you need some kind of depth, multiple levels of representation. And I also believe that somehow these representations, either explicitly or implicitly, must capture the explanatory factors. That's what makes it easy to generalize. If you understand completely the scene, then some new configuration is going to be easy to explain as well. All right. Moving in that direction, a few years ago, we tried to use these unsupervised pre-training trick, which has been sort of this starting approach to deep learning, where we train deep nets by unsupervised learning of like RDMs and denoising encoders. In two competitions, two transfer learning competitions, where you have training data of, including examples of some classes, but the test data really has new classes you've never seen. And your job is to come up with representations for the test examples, such that a very simple linear classifier trained on like 1, 2, 4, 8 examples is going to be doing a good job. So on this graph, this is the log of the number of labeled examples on the test set that are used to test your representation. So 1, 2, 4, these are on log scale. And the y-axis is some measure of accuracy, so 1 is 100% accuracy. And these curves show one data set where the effect of depth is amazing. And this is if you put your classifier directly on the raw data. This is if you put your classifier, so you'd like the curve to be like this one, to rise up as quickly as possible. If you put it on the first layer, which is trained completely unsupervised, and then the second one, and the third one, and the fourth one. So somehow by learning these deeper representations, in this case, the effect on your ability to generalize from fewer examples is absolutely amazing.
So if I can read those axes,
Yes.
on the one on the right, after one example, you're at 85% performance, and after two, you've done that at 98%.
So this is log scale. So this is one labeled examples per class.
Yep.
This is 2 per class.
Yep.
Right. So here you've got, say, 4 examples, and you're getting whatever.
That's true.
95% accuracy, essentially.
How different were the classes,
So the interesting thing about this competition is that we didn't know what the data was. So the data had been obfuscated, so no one could use their own human prior knowledge in order to cheat into some good representation. The idea was, can someone come up with a completely ab initio learning of representation? And that's what would be evaluated, rather than, the way we usually do things in machine learning is we have, lots of students and engineers coming up with good features, and that's what, is competing really, and not with machine learning.
But do you still have a sense of what the class is?
Yeah, so there were 5 data sets, for example, in this one, some text, some video, some image. This one, I think, is features coming of looking at satellite data and trying to classify into the types of trees and stuff like that. Now, there is an interesting question that is, what is a good representation? I mean, if we're going to be learning representations, what makes a good representation? Of course, we could say, well, if we use a representation in a classifier and it does well, okay, that's an easy answer. But is there a more fundamental question we could try to answer there? There is something related to this question, which is a very important notion in computer vision, and maybe to some extent in speech recognition, which is how do we design features that are invariant to the things that don't matter? Like I would say in speech, that would be maybe the microphone characteristics or the speaker. But really, if you're doing unsupervised learning, nobody tells you what variations matter and what variations don't. So what can you do? In that case, you don't really want to do invariant learning because it doesn't even make sense. You don't know which variations matter. Like, you don't know if you're going to be using those features for speech recognition or for speaker identification. So you shouldn't throw away that information. You should just keep it, but somehow separate the characteristics of the signal that tell you about the speaker from the characteristics of the signal that tell you about the phonemes. That's what you really want. And you want to do that automatically without having to tell the machine. So that's what I call disentangling factors of variation. And I don't know how to do that, but that's what I would really like to have. Machine learning that discovers the underlying factors and separates them out. And maybe it's not going to do a perfect job because it doesn't know what the true factors are, but maybe there's something in the statistics of the data that gives you strong indications of what these factors are, and they have some kind of orthogonality or independence that you can exploit. It turns out that when we use our classical techniques like RDMs and autoencoders, some amount of disentangling is happening. In other words, that if you know that about some factors and you look for them in the features, you find some features more correlated to some factors and less correlated to other factors as you go higher up. So some kind of disentangling is going on, but we don't fully understand. And my thinking is that we won't be able to do this really well in general in a completely ab initio way. We need some kind of priors to help the machine figure out what disentangling even means. So so I've listed here a bunch of these priors. One is that there are such factors, right? That they exist and somehow they can vary separately. Another one is that they organize themselves at multiple levels in a kind of hierarchy. Another one is that if you have classes, then those classes, the identity of those classes is one of the factors explaining the data. Now, it doesn't have to be that way, right? That's the assumption that you're making in semi-supervised learning. For example, you could have, what I'm saying is, you could have P of X and Y being decomposed as P of Y given X times P of X, where P of X has nothing to do with Y. In which case, you couldn't do semi-supervised learning. The only reason you're able to do semi-supervised learning is because P of X contains information about Y. That, for example, there are natural clusters, and so if you can identify these clusters, then it becomes easier to classify. This prior tells you that if you have different tasks, that they share some factors, that some subset of factors is useful for some task, and another subset is useful for another task. So this is the prior we use in multitask learning. Another prior is the one we find in the manifold hypothesis, which tells us that in the kinds of data we care about, probability is concentrated. That most configurations are unlikely, and probability is concentrated in these typically low-dimensional regions. Connected to this hypothesis is the natural clustering hypothesis that tells us that, well, these regions of concentration can be interpreted as classes, and we can call them manifolds, and these manifolds are well separated by regions of low probability. Another interesting prior is the temporal and spatial coherence prior, which has been exploited for a long time, as well as a long history behind this. For example, all the work on slow features, it's exploited in, for example, convolutional nets because of spatial coherence, and in many guises this comes up. Sparsity is one of the priors that people in the deep learning community have kind of hit on, and that's interesting. And you can interpret it from as a prior by saying that most factors, for a particular example, most factors are irrelevant. So if I give you an image, it's an image that's outdoor, so it doesn't contain indoor things. And so a lot of the concepts that matter for indoor things don't matter there. And then there's an interesting prior here, which hasn't been discussed as much, and but I think it makes a lot of sense, which is that in a good representation, the distribution of the factors should be simple. So the extreme case is that the factors are independent of each other, but you could have something not as drastic. For example, you can imagine having just linear dependencies between the factors. And that's what the Mikolov example is actually exploiting. The way he's training these is that he's looking for linear dependencies between the embeddings of successive words. And I believe that by doing that, he's kind of regularizing in some way and getting these nice analogies coming up more easily. All right, see the time is flying. So let's go to unsupervised learning. So unsupervised learning would be great. I mean, we can exploit more unlabeled data. I think it's really important for transfer learning, for answering new questions and not just always the same old question, for structured output problems. But it hasn't, I don't see Google using this right now. I don't see Microsoft using this. So why is that? So I think there are some fundamental problems that make unsupervised learning, especially of probabilistic models, really hard. And here I'm trying to explain them. One is the problem of mixing between modes when you're running, trying to sample using a Markov chain. And the reason it's hard, it has to do with the manifold hypothesis that I mentioned earlier. I'm going to go into more detail on that. And the other is that the number of these modes, so the modes are the regions of high probability that I was talking about before. If there's a huge number of them, then either in the posterior or the joint distribution we care about, then modeling these distributions, these joint or these conditional distributions could be really hard. And again, the sampling methods are going to fail. So let's look at the first problem. So this is meant to be a distribution over here, a one-dimensional space, but think really a high-dimensional space, and these are the modes, okay, those regions, those peaks of probability, those regions of high probability. And MCMC operates by moving around in that space, by making small steps. And the problem is that it only goes from it only wants to go to a probable configuration. That's what MCMC does. It wants to stay in the regions of high probability. I mean, if you start it in the low probability region, it will move towards a high probability region, and then it will stay there. And it will be very hard for MCMC methods to cross the desert of low probability, because it would be exponentially unlikely to do all of these unlikely moves one after the other. So that's bad, and it's particularly bad if you use these MCMC methods in the middle of your training procedures. It turns out that for many of our unsupervised learning procedures with probabilistic models, like Boltzmann machines, that's what you're doing. Initially, when you train a probabilistic model, It doesn't know anything, so it says, I'm happy with everything, everything is probable, I like the uniform distribution, and it's kind of flat, and then you can mix easily, you can move around, and as it learns, it starts putting, more concentrated probability in a few places. It still mixes fairly well. So initial training of RDNs and stuff like that works quite well. But then, as it gets good, it has to put low probability in more and more places, and that's where it gets harder to train, because now these MCMC methods we're using to get the gradient, they give us a very noisy estimate of the gradient, and so I think training stalls. So let me tell you about something related that may help us to fix this problem. So we tried to do some kind of visualization to understand what is going on with those representations we are learning with stacks of RVMs or stacks of denoising mode 1 coders or contracted mode 1 coders, whatever. And what we find is that the space is kind of distorted by these representations. The shape of the distributions in input space is very, very different from the shape of the distributions when you take the data and you move it up to these high-level representations. And so this slide is supposed to illustrate that. Let's look at the top here. So here, I'm showing in input space, so this is pixel space, say images of 9 and images of 3. This is just a cartoon, of course. The distributions are very concentrated, and there's a lot of empty void, and it's hard to mix between them. And it looks like when you project the data onto the hidden units higher up, you see the distributions now where the data is occupy a lot more volume, and those things get closer to each other. And furthermore, it's like if those manifolds where the data is lying have become flat. So let me explain what I mean. So in input space, it's like the regions of high probability, these manifolds are highly curved, much more than that picture. They really have a lot of curvature. It's just wiggling all over the place. So if you take any two examples, think about two images like the 9 and the 3 here, and you do a linear interpolation, and you look at the image in between, you get something that's unlikely. Like, to just add two images, you get garbage, right? It doesn't look like a real image. In fact, you know that it's a mixture of two images. Whereas if you do the same thing in the space of the learned representations, the image in between looks like a likely image. So here, if we take this 3 and this 9, and we move it up to the higher level representation, and then we add them up with different coefficients, we get all of these images which all look like fairly plausible digits. So what it means is that although in input space the manifolds are highly curved, in the high level space it's like this curve is like a straight line when you move in the representation space. And that's great. That's great because now it's much easier to do all kinds of things to mix in particular when you are working at that level. Let me say a few words about the other problem of having yes?
Before you go on, could you spend a minute telling me, for example, for that interpolated representation, how do you synthesize the image? I mean, I can imagine what it might be, but I'd like to know.
Yes, okay, sorry, I should have been more precise.
Yeah.
So you take your image, you move it, you compute its representation. Now you have two images, you have the representation. Now you can mix them at that level, like just do linear interpolation. And now you've got these vectors that are just abstract vectors. And you can use the decoder, you can use the decoder to map them back, or the generative model to map them back in input space. You've got a node encoder, right? So you've got a mapping from X to H and a mapping from H to X.
Okay, so you keep the mapping from H.
Oh yes, you need both mappings for this to work. You need the encoder to go from input space to representation space, and you need a decoder to go from representation space to input space. And then you can visualize the interpolated points in representation space as images that make sense to you.
And here in the representation space, you're looking at the highest layer?
Yes. Actually, you can see this is first layer, second layer, right? The higher you go, the better it is.
And I suppose the other way to do it, if you didn't have the decoder, would be to sort of start playing with the input till you get.
Yeah, you could do that. You could do that, but it's so much more convenient to have a decoder.
So can I ask one?
Yeah.
So the fussy maps or isomat or any of those
Yes, yes,
really
yes.
do the same thing, right? So the question.
Except they do it wrong. But
Well,
yeah.
so that's the question: is what about the neural net
Yes.
architecture do you think is
Right.
supplanting this notion of local graph structure and your
Right. So the training criterion for things like Laplacian eigenmaps and other manifold learning methods is fine. It's not the problem. It's the parameterization. The parameterization is this basically a sum of Gaussian. It's a dumb non-parametric model. And what it does is that it doesn't generalize. It only generalizes very locally. So in other words, to capture the structure of a highly curved manifold, you need, use this. If you have a highly curved manifold, you need enough examples to cover all of the curvatures, all of the curves of the manifold. And if you don't have examples, enough to cover all these variations, you're going to do something completely wrong. Whereas with these neural nets, you have a chance, if there is some structure in the data, and your model can be trained to capture it, to actually generalize to new places you haven't seen. And we verified that it works. For example, you can train on some digits and then generalize to other digits it's never seen, in the sense that it knows the shape of the manifold in new places. So and the reason it can do that is because it's assuming that there are these underlying factors that are can vary independently. And if there is such a thing, and there is in many data sets, then it can generalize to completely new configurations of these factors that it has never seen before.
So how do you impose any sort of locality that can never see your graph?
Oh, you get locality automatically for almost any machine learning method because it likes smooth continuous things. So that gives you locality for free. And the reason it likes smooth continuous things is that they're easier to learn, right? So when the weights are small, you get smooth functions.
Okay, but so there's a regularizer.
Yeah, there's a regularizer. In almost any machine learning, that you want to do, you end up having a kind of smoothness regularizer, implicit or explicit. Here, it's just the magnitude of the weights which give you this regularizer explicitly. More questions on this picture, which seems to like? All right. So let me move on to something else. So I mentioned there was another challenge, which is that you potentially could have a lot of modes in your distribution. And let me just skip quickly. So here again, it's a cartoon, but imagine your distribution have many modes. That's P of x, and this is going to be a problem when you sample, and it's going to be a problem when you learn, because especially when you sample, because or when you train, it's going to be hard to generalize to new modes. It's going to be hard to avoid spurious modes. It's going to be hard to even mix between all those modes when you're training. So instead, we consider a slightly different problem, which is the problem of learning a Markov chain that whose stationary distribution would be the same that you're looking for. So you're looking for some distribution, trying to estimate a distribution, but instead of representing P of x directly, I'm saying, well, why not representing the distribution implicitly through some conditional transition operator that tells you how to move from one point to another point. Now, the advantage of this in terms of dealing with the modes is that this conditional distribution only needs to look at few modes. So in particular, the normalizing constant of a probability distribution, the partition function, which comes up in the gradient, has to consider all the modes. But if it's a conditional distribution, the normalizing constant is only over the the modes that, or the higher probability regions that matter in the context of the right-hand side. So if I'm going to move from a point to some neighboring point, then the conditional distribution here might only have two major modes, and the other are kind of negligible. And so getting the partition function for this conditional distribution right is going to be much easier. Either I can even do it analytically, or I can do some MCMC or something, but the MCMC is going to be much easier because it's going to have to only visit a few modes before I get my gradients to be right. Whereas if I try to learn P of x directly, the gradient of the log likelihood involves summing through all the modes, and that's going to be just much harder. So that's the idea of what I call generative stochastic networks, where instead of parameterizing P of x, we're parameterizing this transition operator. And the more general way of seeing it is we also introduce some latent variables in the Markov chain. So now we have got a Markov chain over some visible variables and hidden variables, and just like we'd have in many graphical models. But the difference is the parameterization is now the parameterization of the Markov chain transition itself. So in this case, I have a parameterization that tells me how to get a new x from the previous h, and how to get a new h from the previous h and the previous x. And if I just sample from these, I can run my chain. So given the parameters, I can sample from the model by running my chain. And now the question is, how do we learn the parameters of these distributions so that at the end of the day, the samples I'm getting on the visibles are of roughly the right distribution. And and one trick we use here, which is useful in practice and has been picked up recently, is that notice how I've decided to parameterize this one, P of h, given the previous ones, as a deterministic function of the conditioning variables and some independent noise source. And the advantage of that is that you can just do backprop when you compute gradients. Anyway, I'll come back to that later. So the answer to my question, how do we train that? It turns out that there's a way to train which works, which is you take an example, you throw it into the Markov chain, and then you change your parameters so that it produces, again, the example with high probability. So if you take a data example, you put it here, and then you just let it run a little bit, and then ask this guy to reproduce the original one, that will make the parameters of this transition operator learn to generate data like the training data. And yeah, I could spend a lot more time to explain that, but let me move on. So you can do this you can use this to deal with missing inputs, structured outputs, basically look at subsets and predict the rest and stuff like that. We've done some experiments on rather simple data sets like MNIST and these images of faces, where we can see that it generates sort of nicely comparable to state-of-the-art learning models for these data sets. And you can also do things like filling in some parts. Like here, I've got an image of a digit, but I'm going to clamp the right-hand side and let the left-hand side be free, initialize it with random noise, and then let the Markov chain run. But this is a conditional Markov chain where I only resample the left-hand side. And you can see it converges very, very quickly. The burn-in is almost immediate. And if there is some ambiguity, like there was an example here, that could be a 3, or maybe it could be an 8. And so the Markov chain will alternate between 3s and 8s. And this is just the Markov chain free running, so it resamples all of the pixels each time. And it will, this is one sample after the other, so it's really mixing pretty fast.
So sorry, the lower half is wrapping around, so we can see
Yes.
the middle. It goes.
I think so. Yeah, it looks like it's
wrapping.
wrapping. Yeah, it is wrapping around. Yes. Yeah, so it's one long sequence here. So you can use this framework to actually explain a few nice things. And in particular, some of you may have heard of dependency nets. So dependency nets were invented by Heckerman and collaborators as a way to train Bayes nets that would be much simpler than the usual ways. And the way you would do it is you would train a separate model, maybe like a neural net, that predicts each variable given the other one. So this isn't the case where everything is observed, and but still learning the joint might be complicated because of the structure of the net. It may have very large cliques, so usual training methods are kind of difficult. But that's easy, right? It's just like any machine learning method that predicts one variable given other variables. But they didn't have, it wasn't clear from their paper and the subsequent work, what is it you're really learning here in the sense of, can you actually interpret this? What is the model that is actually being learned? Because these conditionals, unfortunately, are not guaranteed to be consistent with a unique joint distribution. So it turns out you can frame this as a GSN of a particular form by saying, okay, so actually this thing is a building block for a Markov chain, which is a Gibbs type of Markov chain. And the theorems we have tell us that as you do a better job of training this, your stationary distribution of the Markov chain is converging to something that estimates the data distribution. And so now you tell me, well, okay, but still, where is this unique joint? Well, actually, if you look carefully, what this joint is a kind of mixture of all the possible orders in which you could visit the variables to decide which you resample. And in fact, the sampling scheme that they were using doesn't work. I mean, it doesn't satisfy the ergodicity characteristic. So they were proposing to iterate one variable at a time in a fixed order, but you actually have to do it in a random order in order to guarantee ergodicity. And then you can show that this way of training, which is just kind of pseudo-likelihood, gives rise to a Markov chain that estimates the true data generating distribution. In general, if you have a way to train models that estimate the probability, the joint probability of some subset given the rest, then you can usually basically extend this and essentially obtain Markov chains that use these condition probabilities to resample subsets each time. And I'm going to tell you about a particular model that we worked on called NPDDM, which is derived from deep Boltzmann machines. And NP stands for multi-prediction. And these are samples from the model. So let me go to the next slide to explain this. So in a deep Boltzmann machine, I realize many of you don't know what a deep Boltzmann machine is, but it's just a big Boltzmann machine, and the Boltzmann machine just has a bunch of stochastic units connected to each other, and there's various Markov chains you can define to sample from it. The most traditional is the Gibbs sampling, where you resample one variable or a subset of variables at a time. But what we're doing here is slightly different. We're taking the energy function of the deep Boltzmann machine and we're training it with a generalized pseudo-likelihood, meaning just what I was talking about, that you're going to predict on some subset of variables like these two guys or this guy, or actually the y here, that we're trying to learn the joint of input, image, and label. So you predict a subset given the rest. And an interesting subset is y given x, but there are all the other subsets that could be there. And you, instead of using Gibbs sampling to predict, which would involve averaging over many runs, we use mean field. So it's just basically like a big recurrent network in which each unit gets updated deterministically based on the layer above and the layer below, and you recurse that many times, and then you just read off probabilities for each of the variables after a fixed number of steps. And you try to make these probabilities high or low to maximize the probability of the correct values of these variables. So again, you can interpret that as a GSN, just like it's just very similar to dependency nets case. The interesting thing is, well, you can now use this for classification, of course, and we can get very good performance with that. So we get something like 0.88% error on MNIST, which compares to previous work on D-Boltzmann machine, where you get 10 point, no, sorry, where is the, 0.95%, right? But the more interesting thing is that if you take the D-Boltzmann machine, if you believe the D-Boltzmann machine story and you sample from the D-Boltzmann machine trained in this way, you get garbage samples. And in many cases, when you train graphical models with the wrong criterion, which is not maximum likelihood, you get this ugly, when you sample from the model, it doesn't always work nicely. This is what happens here. So this pseudo-likelihood training, this doesn't work as a way to train a good generative model. But if you interpret this as a GSN and you sample by this Markov chain, then you get nice samples. So it's just that you have to match your training criterion with what is the underlying generative model you're really learning, and then you get things right. Okay, let's skip this. I mentioned this nice trick, which basically we came up with in 2 recent papers, including the GSN paper, where you take latent variables that are continuous and you reparameterize them as deterministic functions of the other variables that you care about and some independent noise source. So once you've done that, you can rewrite marginalization. So let's say I want to predict P of y given x. I have to integrate of all of these h's. And so this is just my marginalization. I have to sample P of h given x and average P of y given h and x. Instead of doing that, you could rewrite it as sample this independent noise source and then just have P of y given this deterministic function, which gives me an h. And now this whole thing is something I can compute derivatives of and basically backprop through this into the computation of h. So if I look at this derivative, for example, it just means sample my noise sources and then just do backprop on the likelihood. That's very, very easy. It says take your noise sources, generate your noise. That will give you values of the latent variables, and just do backprop into your model of the likelihood, which now is something you can compute. Whereas if you had the kind of sampling view of things, it wasn't obvious you could do that, but you can.
Should we think of this as analogous to importance sampling?
No. You could also do importance sampling on top of that, but that's more like how you can backprop into. So for example, the way we trained this big thing here is we have a target for this. We want to maximize likelihood of somehow the correct answer here. We just backprop to this as a big recurrent net that has noise injected in it everywhere. And so you can, you don't need to marginalize explicitly. The only thing is you sample your noise. That gives you now kind of deterministic computation from input to output. And this is like a big denoising encoder, by the way. And you just backprop to the whole thing in order to train. So that's much easier to train.
It's really not clear to me how this works, like for real data. Surely to generate a particular data, you need particular noise.
Oh no, the noise is blind. It's like Gaussian or setting some bits to 0. It's like in denoising encoders. The noise actually has to be as generic as possible. Yeah, you don't want specific noise. You don't want. I think I've taken enough time now, and just to conclude, deep learning has matured from the early years, 2005, 2006, when we started this. Lots of industrial applications, as you know, but I think there's lots of really exciting challenges ahead of us. One question is, how do we really learn better abstract representations? And that's, I think, is going to be very important to deal with the cases where generalization is difficult. When you want to generalize to new classes, new domains, non-stationary situations, and so on. And the other aspect of my presentation was when you want to do unsupervised learning in many probabilistically motivated approaches, you end up having to deal with these intractable sums. And there are many approaches that have been proposed, and I'm suggesting that maybe we can reframe the way we do things, where we learn directly to generate the data, rather than learn a probabilistic model that has, an analytic formulation for P of X. All right, and I want to thank a lot of people from my lab who have contributed to this work.
So while we have to be out of the room in 10 minutes, we do have some time for questions for people who can stay, which is probably most people. I don't think we have any classes till 1:40.
Okay.
It certainly is a dramatic improvement from what seemed to be in the previous era prior to what you're talking about
Yes.
today, not particularly new ideas, let's say. And I wonder whether the following kind of question has also seen dramatic improvement, which is understanding why the networks do as well as they do and why they fail or they fail. You can imagine a competition where everyone's given a very successful network, and what you have to do is explain why it works.
Right.
So I just wondered to the extent there has been conceptual, technical improvement on that.
So let me try to answer your question. Of course, I think a lot more needs to be done in the direction you were talking about, of understanding. One thing we've done is we've run some hypothesis testing experiments to try to understand why this unsupervised pre-training scheme works so well in some cases. And one of the conclusions is that there's a strong regularization effect. You can really show that the pre-training acts as a regularizer, and so that's interesting. That's one part of the story. Another part of the story is more connected to the optimization problem, which is, I believe, one of the great challenges ahead of us, how to better train these beasts. So even if you have infinite amount of data, forget about regularization. How do we train these models well? Whether they're generative or they're discriminant. Actually, it's easier if they're discriminant. There are these, they seem very hard to train, and we can get stuck in what looks like local minima. We don't even know if they're local minima, and I now believe that they're not local minima, they're saddle points, but that's something that needs to be evaluated. So there's some understanding that's starting to emerge, but it's still a lot of questions. But it looks like, for example, these unsupervised training procedure act as good initializers that get you in the right regions from which initialization is easier. And we now understand that it has to do with, it may have to do at least with just some numerical issues with the gradients being propagated and the eigenvalues of the Jacobians as you go from one layer to the next layer being close to 1, being a good condition. So if you think about an autoencoder, a good linear autoencoder has all its eigenvalues 1. It's trying to learn like the identity mapping. And it turns out that this is a very good condition for the gradients to be propagated across many steps.
So I think, so I have a big broad question. So if someone has a short question, they should go first. Okay, I'll go. So one, from a modeler's point of view or problem solver's point of view, you have, you want to learn representations, you want to learn good models to solve your problem. You have two things you can tweak, right? So one, you can add bias to try to add structure that you think is true in the data or in the domain, and the other is you can change the data, right?
Yes.
You can give it more data, less data.
Well, there's a third thing, which is you can get a better learning algorithm.
You need an optimization. Then there's optimization error. Let's assume we have all the possible tools under the sun to solve any optimization problem we want, which is not true in practice, but let's assume it exists.
Yes, I wish. Yeah.
Right. So now my question, Doctor, is basically, so here, can you speak a little bit to, it seems like, it learns factored representations really well. In the case where you have static data like objects, these are fairly rigid, these are rigid structures, there's variability, but there's variability of certain kinds.
Yeah.
And those kinds of variability can be accomplished using these, factored stacked models. But But for instance, if you
Well,
look
we
at
don't know
domains-
that, but yeah. it's
Yeah, we
something-
don't know that.
They do a reasonable
It
job.
seems like
Yeah.
it's looking better than it looked
Yes.
maybe 5 years ago.
Yes,
But if you look at domains like, say, for instance, activity recognition, and
Yes.
I don't mean activity recognition with the, 5 gestures, the person-centered. I mean in complex, really complex data sets, there's a lot more variability there, and so to some
Right.
extent there's the data bias, right? So one question is, to what extent can you introduce new kinds of biases? The framework allows you to introduce new kinds of biases easily, and you spoke about this.
yes.
Yep,
Yeah.
that one. That's right.
So I'm really interested in broad priors.
Right.
Of course, if you have a specific problem to solve, you can use the specific knowledge in many possible ways, and you can do all kinds of engineering, and it's great, and it's going to help you solve your particular problem. But what's more exciting is to come up with priors, or prior knowledge that you can put in your learning algorithm that's covering a lot of ground, that many tasks will benefit from. And that's the kind of thing I'm trying to list here, and I'm really glad to see more stuff added there. The broader it is, the more interesting for AI, because I'm really interested in AI, not just solving a particular problem. And for AI, you need, unless you imagine you have a zillion of these things that are very specific, and I think that's not what's going on in your brain. You probably have a few tricks that your brain is exploiting, a few priors that help it. And that's what we should be looking for. And these priors, it's not just the priors, it's how convenient it will be to put in the learning algorithm itself. So the notion of learning representations is interesting because many priors can be put in quite naturally there. But yeah, I don't have a general answer besides this kind of stuff.
Right,
Yeah.
so as long as your problem still involves these priors, it's something that right away is ready to use. But if it involves more than that, then the question is, I guess you'd be building some, model on top. Just like people do
It's
with language
all-
modeling and things like that.
It's all tinker toy, and
Yeah.
I don't know. There's no general recipe. Jason?
So maybe there's time for one other broad question. So the brain is not getting IID examples.
Yes. Yeah, that's a great question. I think that besides the interesting sort of learning theoretical things you could say about non-IID data, the real key is to learn representations that will allow you to generalize even though the distribution has changed. And that's where learning good representations becomes important. So we have to adapt the way we learn, we have to handle the sequential aspect and so on. This is all important. But learning good representations in the sense of extracting more abstract characterization of what's going on, I think is going to be key for doing well in a non-IID setting.
I have a question about your recurrent networks and training back
Yes.
in time.
Yes.
How quickly do you lose strength? How many?
We've made a lot of progress with that.
Mhm.
So I worked on this in 1991, and there was a paper in 1994 showing that when you train with backprop through time on very simple problems, after 10 or 20 steps, you're kind of dead. Then came LSTM in the late 90s, and for some of these problems, they were able to train 50 steps, 100 steps, and we still don't have a good understanding of why they work, I think. And now, in recent years, there's been a few more tricks added to the bag of tricks for training recurrent nets that allow us to, in some cases, to train over hundreds of steps quite well and to generalize over thousands of steps. Now, these are very specific, simple problems, and I don't want to make too grandiose claims, but there has been progress, and there's interestingly a lot of work, a lot of people looking at this, and I think there will be more progress in the next few years.
Do you feel like you have the right kind of computer hardware nowadays for
No.
these types of problems? Or is there a different kind of computer hardware you prefer to have available?
Yeah, 10,000 times faster, that's what I mean. Yeah, seriously, we're limited by the computing ability that we have right now. All of the better models we have, we know we could get better results if we could train a model that's 10 times or 100 times bigger. So clearly, there's a much more pressing need now than ever for specialized hardware. So we've already benefited. We've seen the amazing impact, just a 10-fold speed up you get with GPUs. On everybody's being impacted by this. If we can get another 10-fold speed up or 100-fold speed up, I think the impact on applications could be amazing. Now, what is the right hardware? I don't know, but I have some maybe clues. I don't think you need 32-bit precision on these weights while you're doing the computations of the gradients. You need to store them with high precision, but the gradients themselves can be very noisy. And we see this by the fact that we can train these nets where we inject noise all over the place. And that means, like dropout and my Gaussian noise, that means you don't need that much precision when you compute the gradients. But so that means the bulk of the computation could be on low precision somehow, either analog or digital hardware. That could give you a speed up. Another kind of speed up is parallelization. Unfortunately, that's harder, and I have some ideas to do that, but and people at Google are very busy trying to move in that direction. But it's not easy to make those algorithms parallelized because the optimization methods are inherently sequential. At least those that work well right now.
So I think I'd better call time because we're supposed to be out of the room. So let's thank Yoshua again for a nice little talk.